For Nassau though, if you work over 7 hours, you guys know that you guys have to take a break, right?
Yeah.
It's required. So you can't like skip your break and leave 30 minutes early. Okay? It's required, not just by us at the college, not just by them at the clinical sites, but by OSHA and health regulations. So over 7 hours, you need to take a 30-minute break. So work that into your clinical time. That's really all I can think about. We're gonna have an advisory meeting in just a few weeks with the clinical site, so hopefully we'll be able to get some more feedback from them. It really is just upper management though that comes to them, so anything that kind of treads up, we'll probably hear within a few weeks. I think it's October 7th, so I'll let you guys know if I hear anything else new. Do you guys have anything for me? Any questions? Yeah?
The Zoom meeting that you held last week regarding the student vaccines, what came of that?
Okay, good question. So, we are gonna do exemptions for the COVID vaccines. The form that you guys filled out initially for Baptist was, I guess, the form for Baptist employees. So we're working on our legal department right now, drafting their own form. It's gonna be very similar to the one that was already filled out. You're gonna fill that one out, email it to me. I don't have the form yet though. You're gonna email it to me and upload it to Complio, and that's gonna be your exemption.
Okay, cool.
So they're not actually gonna approve anything or decline anything. It's gonna be the college basis, and we're willing to work with you guys, so.
Awesome, thank you
Yeah.
so much, I appreciate
You guys got my announcement about the no delay in waiting to get the flu shot, right? So just to clarify, we were waiting on the WHO, so the World Health Organization, to pair up with the CDC to drop the regulations in accordance to wait to get that flu vaccination. It used to be a month, then they switched it to 2 weeks, now they've cleared it. So you don't have to wait. If you're in the middle of a COVID vaccine, you can get a flu shot. If your physician advises differently or you would like to wait, email me and we can discuss it. I just need to let your site know that your flu shot's gonna be delayed a little bit. But you still need to be in compliance by October 1st unless we speak, okay? October 1st.
Just one thing, can we, like, what if we don't wanna take a flu shot either?
I know, there's no exemption for it. So there's never been any kind of exemption or declination for the flu shot, and there's not even for their employees. Even if you have an egg allergy and you can't get the actual physical immunization, you can always take the nasal mist that doesn't have eggs in it. So they don't consider anything for this. There is no declination or exemption in the flu shot. It kind of stinks.
I think the nasal test has got the live.
They're both live, yeah, they're both live viruses, so, the only difference is the nasal mist, they kinda insert it in and you have to kinda suck it into your body. My kid just got one though, and he doesn't feel good, so wait until the weekend if you're getting yours. He feels really yucky.
So you said for the COVID vaccine, there's gonna be an exemption form that you fill out, so what, you don't know when that's gonna be?
So they're working on drafting it, your due date's gonna be November 15th, so give us a little bit of time. It's gonna be very similar to the one that Baptist provided though, but if you haven't filled out a Baptist one, don't, because it's of no use anyways. But we're gonna draft up our own exemption form, you're gonna email it to me, I'm gonna send it to who I need to send it to, and then you will upload it to Complio as your exemption.
Okay, and what if the form isn't, here before the deadline?
It will, it'll be here like within a week or two.
Okay, cool, thank you.
Yep.
Thank you.
Yes, yes, yes. Anything else? Alright, let me go up to my office and grab some markers because all those are dried out and I need the board today. But we're gonna start out in rad protection. Then we're gonna go into pathology, chapter 3. I gave you guys a common pathology list. If you wanna look at it, you can. You might already know some of these from going through positioning and Bontrager. These are common ones that we need to know specific for radiography and to pass the registry. So like I said, there's a lot of filler. This chapter in pathology is the one that we're gonna cover the most in depth because we perform chest x-rays all the time, but there is a lot of pathology in there that we're gonna skip over. So we're gonna gear more towards what's on the list, and I'm gonna read kind of through and tell you guys which ones we need to know, which ones we don't need to know. So we're gonna start with RadBio, then we'll go into pathology, and I wanna kind of recap and regroup on chest positioning and, chest image analysis while we're here in the chest chapter, just to make sure you guys are solid. If we have time, which I don't think we will today, we'll go up to the lab and we'll do some skull positioning. But just kind of bring your bone trainer, especially if we're doing pathology, because I wanna recap and clear up any gray areas of positioning while we're working on that body part. Any anatomy questions, anything you guys wanna talk about, okay? All right, hang out for just a second. Let me go get my expos.
While she's gone, I'm gonna try to figure it out. Cause I just try to open it from Google, because I was like, oh, it's not sending me just to some other people, you know, like some like everything USB. And so I tried to click on it, it was like, file is too large. I was like, what? So I had to log into my computer.
What does that even mean? I see that. You're gonna see me on my Florida woman. Couldn't have it. I would lose.
As a student, you have your student, I mean, your student email with your whole student email, you get.
Like, I pretty much live my life.
So if you copy it there, you can translate it.
I can't.
Copy paste, copy paste, and then you save it as PDF from, Microsoft Docs.
Send out the same.
No, don't. Oh, cause it saves it to your.
No, it doesn't save it to my work. If I save it as a PDF, that's supposed to be great, but if I send it out.
Well, I have a USB.
I didn't.
It was 64 gigabytes. Then you the day I decided.
Well, you guys don't need cause the only reason I have one gigabyte now is I still have one gigabyte.
And then my hair was real.
Oh, I say all. I say the ones that I get to my English.
This one.
Yeah.
Emo.
Oh, yeah. We could just take it off, just set it over there. Or, no, she's gonna be up there. She's gonna be up there. She's just gonna be up there.
Seriously?
I mean, I get.
Their legs should be
I mean, is she gonna be able to
Had it up in your leak.
You know what? She's gonna be sitting like this. If she's over there, I'm just there. No, you need to sit on the water. Just sit on the water. Like this.
Y'all, I'll move what she had. Y'all can literally just turn.
Oh, no, I'm just my back.
If you turn it, then let me know. Because that would probably.
But if I need to write, I can write backwards. Sure you can. Come on. What do you
Like,
I'm not gonna write on there, just if you need me to illustrate something.
Oh, okay. I'm just gonna
I
come
mean, I'm not
over.
gonna be like manuscripting.
We're trying to be prepared. You can just, thanks for that.
Just relax, we're gonna make it.
It's kinda hard sometimes.
All right, so let's start out chapter 2 in rad protection, RadBio, whatever you wanna call it. All right, so the title of the chapter is Radiation Types, Sources, and Doses received, I'm sorry. So first let's start out, what is radiation? You guys remember? Somebody give me a halfway good definition of it. Kinetic energy is what the book says, but what did you learn in physics? Oh gosh. Alright, let's reword that. What should you have learned in physics?
I'm sure I learned it, but remembering it is the problem.
Instead of making some breakfast or taking care of a cat or whatever. Okay, ionizing radiation when you lose an electron, good. So when it ionizes, it pushes out an electron, interacts directly with the cell, good. So radiation, I would give you this definition just to kind of jog your brain back to physics. Radiation is when energy is emitted and transferred through matter. So radiation is when energy is emitted and transferred through matter. Just to kind of go back to the basics here. It tells you in this little subsection that radiation is kinetic energy and it exists in many forms. Obviously it's kinetic. Radiation is on the EM spectrum. How fast is everything moving on the EM spectrum? Speed of light, good. Now we're tracking a little bit, yay. So exciting, guys. All right, so it tells you at the very top here that some sources of radiation are considered natural because they're always present in the environment, and others are classified as man-made because they are created by us for specific purposes. Hello, what we're doing today, right? What we're doing in X-ray. So these are man-made X-rays or radiations that we are producing. CT would be another example. We're going to talk about another kind of man-made radiation versus natural today. So first let's talk about the EM spectrum. The EM spectrum, by the way, you do not need to know the formula for objects with mass kinetic energy is written as kinetic energy equals half mv squared. We don't need to know that, so X that out or cross that out, whatever you need to know. But we are going to talk about the EM spectrum. So it's a full range of frequencies and wavelengths of electromagnetic waves known as the spectrum. Now the one that the book gives you is really, really basic. So if you flip the page, you can look at it. It's on page 18, if you're in this white book with me. It's very tiny and not explained very well. Very, very basic here. But we know that everything is traveling at the speed of light on this spectrum. But what do we consider their speed? What is a term that we can use for their speed? Anybody? What's a fancy term that we can use? Velocity. Velocity. So their velocity is the speed of light. All right, velocity is the speed of light. Everything on the EM spectrum, velocity is speed. So speed of light. It also tells you that the electromagnetic spectrum shows different radiations in terms of frequency, which is given in units of hertz. So you need to know that frequency is documented or measured in hertz. So it's abbreviated HZ. I'm still on page 17. And then wavelength is measured in meters. So the length of a wave is measured in meters. And then energy is measured in electron volts, or EV. We don't need to go into any of the other information about kinetic energy. But each frequency within the spectrum has a characteristic wavelength and energy. So they all have different wavelengths, they all have different energies, but they're all traveling at the same velocity, which is the speed of light, okay? Everything on the spectrum, speed of light. All right, but then it says note that higher frequencies are associated with shorter wavelengths. So the higher the frequency, the shorter the wavelength you have. So think about it. If we talk about energy, the wave is moving more frequently, it's going to be shorter. If it's moving less frequency, it's going to be longer, right? Are you tracking? A bigger wave, we're moving slower frequency, faster wave in frequency, shorter wave length. So they share an inverse relationship. Inverse relationship. So frequency and wavelengths share an inverse relationship. But then it talks about energy having a direct relationship with frequency. So the higher the frequency, the higher the energy. Higher the frequency, higher the energy. So it's really energetic. What is it?
What was that one for?
Direct relationship, energy and frequency.
Thank
Yep, direct relationship, energy and frequency. Inverse relationship, or inverse, is frequency and wavelength. It writes it kind of funny in here, so that's why I put the notes for you guys. All right, but their velocity is equal to the speed of light, so they all have that common characteristic. Everything on the EM spectrum, velocity is the speed of light. And it even gives you the speed of light, and you need to know this one. It's 3 times 10 to the 8th power meters per second in an empty space in a vacuum on page 17. So 3 times 10 to the 8th power meters per second in an empty space or a vacuum. If you don't have a vacuum, if you don't have something encapsulating it, there is nothing. There is no EM spectrum. It has to be secured in a vacuum. If there is no vacuum or no tube housing, no glass tube, you have no radiation. Okay? Has to be present within the vacuum. Okay, then it breaks it down into ionizing versus non-ionizing radiation. Ionizing versus non-ionizing radiation. So the first ones they list, turn the page on page 18. X-rays. Hey, they love us, right? X-rays, gamma rays, ultraviolet waves with energy greater than 10 electron volts. These are all ionizing. And then non-ionizing on the EM spectrums are ultraviolet radiation with energy less than 10 electron volts, visible light, infrared rays, microwaves, and radio waves. And it says if electromagnetic radiation is of high enough frequency, it can transfer sufficient energy to some orbital electrons and remove them, classifying them as ionizing radiation. So when the radiation interacts and bumps out an electron, it's considered ionizing. If it doesn't, if it just passes through the matter and hangs out, it's non-ionizing. When we start moving electrons and start ionizing cells in our body, cells in animals, matter in food, things start getting a little hairy, and we risk interacting with the cell and possibly damaging it or breaking it. All right, so once we get off of the EM spectrum, because everything on the EM spectrum is light, meaning nothing has weight, okay? It's not weighted at all. There's nothing of weight on the EM spectrum. It's just waves, right? Electromagnetic waves on the spectrum. So when we step off of that spectrum, when the particles start gaining mass, we run into something called particulate radiation on page 19. Particulate radiation. So particulate radiation differs from the EM spectrum because it has a mass. So we've gained something. We've had an interaction, we've picked up another electron, we've picked up another proton, we've picked up another neutron, we've picked up something to gain some weight. So we're getting a little heavy. We're not on the EM spectrum anymore. We are now particulate radiation. It breaks it down into a couple different categories. So we have alpha particles, beta particles, neutrons, and protons. So these actually have weight. Anybody remember from Physics 1, since I am teaching it, my brain's kind of fresh in it. Remember, you cannot split or break down an electron, but you can split or break down a proton or a neutron. Anybody remember that? When you split or break down a proton or a neutron, what is it called? No, it's called a quark. So Q-U-A-R-T. Quark. So we can't break down any electrons. Electrons are solid, small particles. But when we talk about the nucleus, which houses protons and neutrons, right? Everybody knows that our nucleus of our atom is a proton or protons and neutrons, right? So it has a what charge? Positive charge. And then we have orbital electrons that are housing it, and that law of attraction is keeping the electrons bound, right? Are we tracking? How about the Bohr's model? Let's get a refresh here. Just because we were having some trouble kind of picturing this yesterday. So the Bohr's model is going to look something like this, where you have a couple of things here. Maybe these are neutrons, protons. So this is our nucleus, right? There's our nucleus here. If we want to kill or interact directly with the nucleus, we have to have some kind of really big particle. So normal X-ray cannot interact with the nucleus. It hangs out and bumps out the orbital shell electrons. Okay, no interaction with the nucleus. The Bohr's model is when you see some kind of solar system. Wow, this is great, guys. Terrible. And this is supposed to look fancy, but it doesn't work, right? This glass. It's not very functional. All right, so we have our little electrons here. They're orbiting around in the shell. The law of attraction is keeping them in. They're nice and cozy. But you guys know that an atom doesn't really look like this, right? Okay, so an atom actually looks more like this. You have protons, neutrons. They may be encapsulated, sure. Here's our nucleus. But an actual atom is going to look something like this. So the orbital shells run in a 4D manner, right? Because it's actually live. So if you see something like this on your registry, and it talks about some kind of X-ray interaction, and you're trying to figure out if it's the K shell, the L shell, the N shell, whatever, it's still the one that is closest to the nucleus. So this is K shell, this is kind of an electron. Let me make it bigger for you. Alright, so if it has like 4 different things right here, the one that is closest to the nucleus is still going to be the K shell. So I've been seeing a lot of registry questions kind of shifting from this Bohr's model to this one. Okay, so kind of get familiar with viewing an atom in a 3D/4D form. Okay, so this is kind of becoming outdated, and especially for us because we're not actually counting electrons, we just know that there's interactions within the electron shells. Okay, so just make sure you know how to identify it in both forms. Bohr's model, named after the physicist Bohr, Niels Bohr, but kind of phasing out there. All right, so we have alpha, beta, neutrons, and protons. These things have mass, so they have weight. But they're all a little bit different. So let's see. I need some people to demonstrate this one. Who wants to be alpha? Who wants to be alpha? You're not going to be doing much. Come on, you're like big and bad. Alpha's bad. Come on. I need you.
I'll be alpha.
Okay, all right, she's alpha. Come up here. Who's going to be beta? All right, come on, beta. All right, who's going to be a neutron and who's going to be a proton? Neutron, you're neutral. Are you positive? Okay, come on. All right, so there demonstrate to you guys what the actual particulate radiation would be doing. So they're still moving at the speed of light when they come off of the spectrum, and they've gained some mass, so they have a little bit of weight. They're real now. They're not just a wave. They're an actual particle with mass, but they're all doing something a little different. So alpha, you are the big guy. So you transfer a lot of energy. So we gotta think of her as like a bodybuilder right now, right? So she has a big punch. She's gonna knock you out,
Yeah.
right?
I'm a big punch, guys.
But alpha can be stopped by paper. So alpha can be stopped by paper. So if I were to rip this out, I'm not going to, hold it in front of her, she wouldn't be able to move, okay? She's stuck here, she can't penetrate. She's large and she's powerful and she can kill you, but she can't pass through paper. So alpha, you're gonna kind of just truck along like this, okay? You're moving like this. That's her alpha valve right here. All right, then we have this person over here who's beta. Beta's a bad girl too, okay? She will mess you up. But you need a block of wood or lead to stop beta, okay? She is powerful. However, she's very, very penetrating too. Not as powerful as alpha, but she's pretty powerful. She's extremely penetrating though, and you're running around. So you are speeding. She's really speeding. She's really speeding. And these guys over here, they're gonna be contained within an atom. So you guys are gonna come over here away. You're together, you're friends. So you're neutral, you're gonna talk her through it. You're positive, so you're gonna encourage her, okay? But you guys are the same weight, and you're within an atom. So you're just hanging out. Your electrons are moving around you, but you're still. All right, so we have alpha. She's our big girl over here. She's the power puncher, can be stopped by paper. She is non-penetrating, but she will kill you, okay? She will kill you, for real. This girl over here, she's racing. She's actually just another form of an electron. So she's orbiting super fast, highly penetrating. So she's able to pass through everything except for a large block of wood or lead. So easy to transfer here. And then these girls over here, protons, neutrons, hanging out together in an atom, not doing much, but they have some weight. They're bigger than an electron. They're encouraging each other, staying neutral, right? But have some weight, could possibly be busted up and broken down into quarks. These guys over here are solid, so you can't break them. All right, thank you guys, thank you. Thank you so much. All right, so let's talk about them a little bit more. I know. Now you guys can talk about your particulate radiation in class today. How fun. All right, so alpha particles. What do we need to know? Paper can stop alpha. Paper can stop alpha. Paper. So that means if there's alpha particles in the room, and I have paper in front of me to protect me, it cannot penetrate. It cannot penetrate. However, this could be very deadly, and I'm going to show you guys a really cool video about an alpha poisoning that took place. So I'll show you the video, and then we'll talk about it a little bit. It can be stopped by paper. You do need to know that alpha is produced by radioactive decay. So radioactive decay. So what is that? It's a natural process that occurs in which an unstable nuclei, so they have some kind of instability within the nucleus. So maybe they have, I don't know, 2 protons and 1 neutron and an electron coming in. Or they have more protons than electrons. Whatever's going on with the nucleus, it's unstable. And then what happens is a nuclear spontaneous emission, which is basically where they're hanging out in the nucleus and they're like, okay, we gotta get out of here. Ah! Okay, so they run out. So alpha's leaving the nucleus, and then they contain 2 protons and 2 neutrons. So they take those guys with them out of the nucleus. Basically, think about it like an explosion in the nucleus, okay? Explosion in the nucleus. Alpha particles contain 2 protons and 2 neutrons. They're created by radioactive decay. They are very dangerous. It talks about uranium being a product of it. You can know that if you want to. A little fun fact. They have a large mass. This is important to know. They have a large mass that is approximately 4 times the mass of a hydrogen atom and a positive charge twice that of an electron. So electrons can be positively or negatively charged when we talk about particulate radiation. So I know that can be a little confusing. It does tell you that particulate radiations vary in their ability to penetrate matter compared with beta, which are just fast electrons. Alpha particles are much less penetrating. That's why they can be stopped with paper. So remember, when you think about penetration and energy, we're not associating that with how fast they are moving, because the speed of light is how fast they are moving, right? So they're all traveling at the same speed, but alpha is kind of hanging out like this. Beta is running in place, burning a lot of energy, right? Highly, highly penetrating, able to go through more things than alpha. Then they talk about beta, also known as beta rays, identical to high-speed electrons except for their origin. Electrons originate in atomic shells outside of the nucleus. They're orbiting, whereas beta particles, like alpha particles, are emitted within the nuclei of radioactive atoms. So they are created by radioactive decay. Radioactive decay. This is important to know. Beta particles are 8,000 times lighter than alpha particles and only have 1 unit of electrical charge, -1, as compared to alpha's 2 units of electrical charge, +2. Therefore, they are capable of penetrating biologic matter to a greater depth than alpha particles with far less ionization along their paths, because they push through, right? They push through. They don't have to stop at the paper. They make it through paper, they can make it through plastic, make it through cloth, make it through smaller amounts of wood, smaller amounts of lead, but eventually they're going to be stopped. And it does tell you the thickness that you need to stop it somewhere here.
5 to 6 centimeters.
1 centimeter thick piece of wood and 1 millimeter thick of lead shield. It's at the very bottom, 2 paragraphs up from the bottom is what it tells you. So it says, such very high energy electrons require either millimeters of lead or thick slabs of wood to actually absorb them. Beta rays are noticeably less probability of interaction with matter because they penetrate more deeply. So they're pushing through so quickly that they're not interacting with a lot of different things. Whereas alpha stops to interact with a lot more along the way. They're a slower frequency but not speed. All right, so let's talk about anatomical mass. How is anatomical mass calculated? Do you guys remember from physics? Something to do with the nucleus. Protons plus neutrons is the anatomical mass. Protons plus neutrons, anatomical mass. There's your little physics recap. How about the Z number or the atomic number?
To do with neutrons.
Just protons. Just protons. So it tells you the Z number or the atomic number is designated and calculated by the number of protons. So if you take a proton out of an element, it changes its form. So everything on that periodic table is named and given a symbol based on the number of protons. So the weight can change. We can have different numbers of neutrons within the nucleus and different masses. But if we change the number of protons, we change the element completely. So that's what happens in radioactive decay. You go from a source called radon to radon gas. So over time, radon kind of decays and loses a little bit of its energy through combustion, and it turns into a gas form. Then we've got protons, which are the positively charged portion of the atom, normally just remaining in the nucleus. And then neutrons, which are electrically neutral. These are our guys that are very neutral, kind of referee, moderate everything. And they are also within the nucleus. It does tell you if 2 atoms have the same number of protons, meaning they're the same element, same number of protons, same element, same Z number, same atomic number, but different number of neutrons, they're referred to as isotopes. Isotopes. How about if we have something that's charged, if we have more electrons than protons in an atom? What is it called? More protons than electrons, or more electrons than protons? Ions? Ions? All right, so isotopes, differing neutrons. Ions is not in this book, but it is in your physics book, and you do need to know it. All right, so isotopes, same element, same number of protons, same Z number, differing neutrons, isotope. If it has a charge, if you have 2 protons and 6 electrons, it is called a negative ion, okay, negative ion. If you have 6 protons and 2 electrons, it is a positive ion. All right, so the charge can take place there. Okay, before we talk about the doses, I want to show you guys the video about the alpha poisoning. That's really cool. Maybe. And I put it on your canvas too. Don't worry about the title of the video or who it's produced by.
It was the shocking murder of a prominent Russian dissident seen here dying in his hospital bed, and an act of nuclear terrorism, say British officials, in the heart of London, just yards from the US Embassy. Now a British investigation has found that the 2 Russian secret agents accused of the murder, quote, probably acted with the approval of Russian President Vladimir Putin.
The FSB operation to kill Mr. Litvinenko was probably approved by Mr. Khrushchev, then head of the FSB, and also by President Putin.
Alexander Litvinenko, who fled Russia for the UK to seek asylum, was an outspoken critic of the Kremlin, accusing President Putin of orchestrating the deadly bombings of Russian apartment buildings in 1999 to justify a second Russian invasion of Chechnya. Another potential motive? Report cites an article Litvinenko published that accuses Putin of sexual involvement with underage boys, and that Russian intelligence had video evidence. Litvinenko blamed Putin for ordering his poisoning and authorized this statement from his deathbed.
You may succeed in silencing one man, but the howl of protest from around the world will reverberate, Mr. Putin, in your ears for the rest of your life.
Today, Litvinenko's widow, Marina, welcomed the British findings.
I'm of course very pleased that the words my husband spoke on his deathbed when he accused Mr. Putin of his murder have been proved.
The details of the case seem stolen from a spy novel. Surveillance video shows the Russian agents at the London hotel where they allegedly injected a powerful dose of the highly radioactive element polonium-210 into Litvinenko's tea during a meeting there. Litvinenko died a slow, painful death, and the radioactive polonium contaminated dozens of other people who had direct or indirect contact with him.
This was a blatant and unacceptable breach of the most fundamental tenets of international law and of civilized behavior.
Today, one of the accused killers, Andrei Ligovoy, now a Russian politician, vehemently denied the accusation.
An outrageous lie, and I can't find any other word to describe it.
Russian officials dismissed the findings as politicized.
This gross provocation of the British authorities cannot help hurting our bilateral relations.
All right. So Russia's kind of dirty, right, guys? A little more than the US at least. So what happened? Basically, this Russian spy, Alexander Litvinenko, met with a couple of public officials in Russia, and he drank some tea with them, and then later on that day, he started feeling like deathly ill. Okay, so he thought that he had been poisoned, but he couldn't prove it. So he went to the hospital, and he said, hey, something's going on with me. I'm having convulsions. I feel like I can't breathe. Something's going on. Well, they couldn't find anything externally. Okay, they did all this blood work, they couldn't find anything, they just knew that he was declining fast. This happened in 2006, by the way, this was not that long ago. So 2006, somebody got poisoned. So when he met with these public officials, they put plutonium or plutonium in his tea, which is an alpha particle, and poisoned him. Now remember what we talked about. Alpha is deadly, but it can't pass through paper, right? So after he died, they cut his body open, they got out a Geiger-Muller counter, which is kind of like a dosimeter. You guys might have seen it running around the department in Nuke Med, something like that. It almost looks like a gun or one of those thermometers that you can read with your forehead. You can kind of test for radiation in the air, so ionizations in the air. They use it in Nuke Med to see if something is still radioactive. Well, when they cut his body open, it was pouring alpha particles. So it was proven that he was poisoned by something. Because the alpha can't pass through paper, it was trapped in his body, killing him, right? So everybody externally wasn't affected unless they actually inhaled it or ingested it. So anybody who drank the tea or sniffed the tea or prepared the tea, whatever, they could have been exposed to it. He did die. They couldn't figure out why he was dying in the hospital though, because it was so contained in his body. But once they cut him open and the alpha was able to penetrate through, then they could detect it. Proven that he was killed by it, not proven specifically that these people killed them, but now they're politicians and Russia's dirty, so moral of the story, don't go to Russia unless you want to be poisoned, right? Yeah. It was kind of interesting though, especially because it was a more recent one in 2006, and they call it an act of bioterrorism. So more and more these days, people are trying to figure out how to kill somebody with stealth, you know? They don't want to use weapons or nuclear bombs, so we can just poison them with plutonium or plutonium in their tea, right? Don't do it though. Don't do it, guys. All right, so interesting story though. He died, I think, within 22 days of going in the hospital, but rapid declining. He was like pouring blood from all of his orifices and not a good situation. And then you could see his wife speaking afterwards saying, the words that my husband said on his deathbed were now proven to be true. But obviously, Vladimir Putin is still the president, and the guy who poisoned him is now a higher official within the government. So, interesting little scandal there. All right, so let's talk about doses. So it gives you a very, very brief introduction here. We're going to talk about these more as we go throughout this book. The concepts are kind of unwrapped in like chapter 9, chapter 10, chapter 6. But they give you two different terms here in the very beginning. They talk about the radiation quantity being the absorbed dose, sometimes shortened for dose. So this is what the patient or what you are actually receiving, the dose. It is measured in gray. So I like to pair these by saying absorbed dose A and gray A. What do I mean? You write it down. So absorbed dose. Absorbed dose. Gray. So pair these two A's together. Gray is the unit of measurement for absorbed dose, okay? Gray is the unit of measurement for absorbed dose. This refers to the amount of kinetic energy per unit of mass that has been absorbed in a material due to its interaction with ionizing radiation. Shortened to the dose that the person receives, okay? The dose that the person receives, measured in gray. Match the A's. A, absorbed dose, A in gray. What is it?
Was that the milligray?
Milligray, yes.
Okay.
Yep, milligray.
I'll try and find what it was.
Okay, then it talks about, well actually before we go down to equivalent or effective dose, let's talk about human tissue specifically. So it says the amount of energy absorbed by human tissue is an important determinant for the extent of the biological harm. So if you receive 5 grays to your eye, it is more detrimental than you receiving 5 grays to your finger. So when we start taking into account different types of tissue, we talk about radiosensitivity of the organ. So what is a radiosensitive organ that you know of? What is something that we shield for? Thyroid? What is it? Ovaries, good. Eyeballs, good. Your eyeballs. Brain is radiosensitive, not highly though, lower than most of our organs. So our radiosensitive organs mainly are eyes that we want to protect. So if you work in fluoro, you might want to invest in a pair of leaded glasses to protect your eyes if you end up working there long term, not if you do one fluoro exam a week. If you work at MD Anderson and you're doing fluoro every day, or memorial within the fluoro room, or the OR, or some kind of special procedures, go ahead and invest, or see if your facility will invest once they hire you for lead-lined glasses. Because now it's proven that people are developing cataracts from repeated dose to the eye. Your skin, or your entrance skin exposure dose, is much higher than what the lens of the eye can take. So once the lens of your eye receives a certain threshold or amount of radiation, you're gonna get cataracts. Things like cancer, spontaneous, things like that are harder to pinpoint. They're considered non-threshold, meaning we don't know how much radiation it takes to give you leukemia, or cancer of your thyroid, or for you to start growing cysts, or benign meningiomas on your thyroid, so things like that. But specifically, yes, your eyes, your ovaries, your gonads, things like that we want to shield. So organs that contain sex cells or germ cells are very radiosensitive. We know that there's a timeline in which we're created that we have to give birth or have children if we want to, without mutations or defects being present. So same kind of thing here. If we radiate those radiosensitive organs, germ cells, sperm cells, things like that, we risk having defects in them. So that is why we shield people. I don't really know why we don't have lead-lined glasses in the department standard though, but I think it will shift eventually now that there's more research on cataracts these days. All right, so when we actually take into account the type of tissue that's being radiated, not just saying, okay, this person received 5 gray or 6 gray or 7 gray, but when we take into account the actual tissue that's being radiated, you receive 5 grays to your eye, or 5 grays to your finger, or 5 grays to your ovary. They classify this as the equivalent dose. So it's abbreviated EQD, the equivalent dose. So this takes into account the type of radiation that is actually absorbed. So what does this mean? What are they talking about? Was it alpha? Was it beta? Was it ionizing X-ray? Was it microwaves? What was absorbed into the body? Okay, the equivalent dose, the type of radiation. This is measured in millisieverts, or sieverts. So you need to know that one. Equivalent dose is paired with millisieverts. Absorbed dose, or regular dose, is measured in milligray or gray. So A match the A, millisieverts for equivalent dose. Then we have another fancy term called effective dose. Effective dose. This is the most accurate dosing. So this dose is intended to be the best estimate overall to harm that might be produced, because it takes into account the given radiation to the human tissue and the body part. So we have absorbed dose, which is just the dose overall. All right, I am an X-ray beam. I'm radiating everybody in this room 5 grays right now. Specifically, I am using ionizing X-ray to you. So now we're traveling into equivalent dose, which is measured in millisieverts. And then if I get very particular and I say I am ionizing X-ray, giving her 5 millisieverts to her eye, now I am effective dose. So effective dose takes into account everything. So what type of radiation is being used, the absorbed dose, and the body part or tissue that's being irradiated. All right, makes sense? We're going to be memorizing all these numbers later, so just a brief introduction. It talks about when penetrating body tissue, ionizing radiation produces biological damage, primarily by ejecting electrons, that is specifically ionizing radiation, from atoms that could compromise the tissue. Destructive radiation interaction at the atomic level results in molecular changes, and this in turn can cause cellular damage. So not every time you're exposed to X-ray are cells dying or are electrons actually being removed, because the ionizations could just pass through and interact with only some of your cells. Sometimes, depending on the content of the radiation, you do have interaction. You could have biological damage, which could then lead to cellular damage, which could then lead to DNA or genetic defects. So know this, the amount of radiation that you receive could potentially affect your children. So that's why sometimes people say, oh, I'm done having kids, I don't care about my organs, whatever. So DNA can actually be affected by radiation in forms. Depending on the higher ionizations, if you're working with particulate radiation or just X-ray, it's gonna differ. It's not like we have to be in fear or scared when we're using X-ray or X-raying people, but know that there can be strand breaks or damage to the DNA, which could then in turn produce a DNA defect in a child. Now, the reason why we talk about this is because of nuclear power plant explosions, atomic bombs, things like that. I've got a cool video on Chernobyl to show you guys too. So this kind of defect wouldn't happen by just receiving an X-ray or a CT. You would need to receive a large whole body dose for something like this to happen. So I don't want to scare you. But it does talk about if excessive cellular damage occurs, the living organism will have a significant possibility of exhibiting genetic or somatic meaning body, soma is the body or tissue, such changes as the following: mutations, cataracts, and leukemia. Mutations, cataracts, or leukemia. And we're going to talk about these throughout the course as well. So let's talk about the sources of radiation. We have natural, which is naturally occurring. We have no control over it. Happens in the world, whether we're here or whether we're not. And then we have man-made or artificial radiation. That is obviously what we produce. On this little chart here, it gives you the average annual radiation equivalent dose for estimated levels of radiation exposure for humans. It's table 2.3 on page 21. I want you to specifically know radon is 2 millisieverts annually. Radon is 2 millisieverts because it is the highest of the natural. And I want you to know the total annual the effective dose from all sources at the very bottom, which is 6.3. So 6.3 effective dose millisieverts annually received by humans for background or natural radiation. So this is something that we don't make. It gives you the sources: radon, cosmic, terrestrial, internally deposited radionucleotides. Then it takes into account CT scanning, nuke med, interventional procedures, radiography. So you can see radiography as a whole is very low, especially compared to CT when we talk about 3 times the dose. So this is why we have places and measures in place to reduce the CT levels, because they are so much higher than just radiography. Nuclear med is just above us at 0.7 millisieverts annually. Remember, nuclear medicine is dealing with the radioactive pharmaceuticals that we actually give somebody, they ingest, we inject them with it, and they're actually producing radiation, whereas our gamma camera is spinning around reading the radiation. So a little bit different production there. So the natural background radiation, still on page 21, it talks about 3 components here. So terrestrial radiation from radioactive materials in the crust of the earth, cosmic radiation from the sun or solar and beyond the solar system, which is galactic, and then internal radiation from radioactive atoms, also known as radionucleotides, which make up a small percentage of the body's tissue. So what? We have radionucleotides in our body, very, very small amounts, and it happens when there's interaction with ionizing background radiation, when we're walking, when we're driving, when we're on an airplane, so things like that. If you travel, you like to hike, the higher the elevation, the more radiation naturally that you would be receiving. So things to think about. So you always have small amounts of radionucleotides in your body because the radiation from the background, the natural occurring radiation, is interacting with your body, and we don't even know it. All right, so it talks about radon here. which is 37% of natural background radiation, primarily comes from the gas radon. Radon. So radon is a noble gas, and that means that it behaves as a free agent and floats around in the soil. So radon never merges with anything. It's not like steam that ends up evaporating in the air. It's not like smoke that can mix with the air and be inhaled. Radon is radioactive, and it is a noble gas that behaves as a free agent, has its own space within the air. It is mainly in the soil. Does anybody have a radon meter in their house? Anybody ever heard of it? Okay. It's common in Florida because think about the sinkholes and how our crust is constantly moving. We're in a peninsula, so we're close to the core and to the, what do you call it? No, the sea level. The sea level. What am I thinking of? We're lower elevation, so we're closer to the core, so we have more exposure to radon. The land sea level? Does that sound right?
We're below sea level.
Yeah.
Below sea level. Okay, maybe that's where I'm tracking. All right, so we're low. So radon is very pertinent in Florida, so important for you to know. If you have a home inspection, somebody at some point has done a radon inspection to test for the radioactive gas. It could be occurring in your crawl spaces and in your soil. Turn the page to page 22 and 23. It gives you a little model of how brick veneer can cover up radon. However, it can't protect you from it. So you have to have some kind of meter or reading initially to see if there's radon present. And then you would kind of go from there. Really, you can't remove it though, so the best thing to do if you had a high reading, or if somebody told you if you had a high reading, is to move. Move. Because they're never going to say, oh, you can't live here because of radon, because you can't see it, so you don't know it's killing you, so they could botch a number, you know, you're dying of
disclosed, like when you buy
it should be legally, yes. It should be legally, yes. Questions to ask once you start working in the field of radiography, right? Track these people. All right, cosmic radiation. On page 23, cosmic radiation. So cosmic rays are extraterrestrial origin. They result from nuclear interactions that have taken place in the sun or other stars. The great reduction at sea level happens because the cosmic rays are not deflected by the Earth's magnetic field, and they must traverse the entire thickness, steadily decreasing in density as they're reaching the surface. So they're coming from really high. By the time you get to us in Florida, they're not even reactive. So very, very low amounts. If you look at the little pie chart, it is interesting, and I think good information there. Again, it tells you that radon and thoron. Thoron is just an isotope of radon, so it has a different number of what? If it's an isotope? Neutrons, good. So thoron and radon, your background radiation, 37% of the dose annually that we are going to receive overall. Occupational dose is really, really small. Space and background, pretty small. Then we have CT, that is a larger chunk here on the pie. Nuclear medicine, interventional fluoroscopy, and then conventional radiography or fluoroscopy medical 5%. Very, very low here. So the main amount of radiation that we're actually receiving through the gas, through the air, radon and thoron, thoron the isotope of radon. And we don't even know it, right? We don't even know it. Let's see if we want to actually talk about any of this. So it goes into man-made or artificial radiation depending on the consumer product. So it talks about on page 24, airport surveillance systems, electron microscopes, ionization type smoke detector alarms, industrial static eliminators. All of these have some sort of radiation that's produced, and obviously it's a man-made object. It does tell you under air travel, a flight on a typical commercial airliner results in equivalent dose of 0.005 to 0.01 millisieverts per hour. And then it kind of gives you a good estimation here on page 25. It says if a person spends 10 hours flying aboard a commercial aircraft during a period of normal sunspot activity, that individual will receive a radiation equivalent dose that is about equal to the dose received from one chest x-ray examination. So here's the catch, the next sentence. During a solar flare, a tremendous explosion on the surface of the sun, however, this dose can be 10 to as much as 100 times higher. So we don't know when solar flares are happening. So hopefully there's no solar flare right near in the air. It also tells you that a commercial flight's crews, pilots, flight attendants, etc., actual radiation exposure sometimes exceeds the workers of nuclear power plants. So something to think about if you ever want to go to flight school or you enjoy flying, you're receiving some form of radiation. And the Federal Aviation Administration and other organizations maintain ongoing programs to monitor this. Just like Landauer monitors our radiation, right? Their radiation badge. It also talks about a little bit of atmospheric fallout from nuclear weapons testing. Know that this changes over time. They measure this over years because fallout happens very slow. As the fallout occurs, it should be less and less and less as it falls from the sky to the earth. No atmospheric nuclear testing has occurred since 1980. Good to know, I would definitely know that. We don't do those atmospheric testings anymore. The next page, it talks about the 3 Mile Island. Basically, it was an explosion in Pennsylvania, but the amount of radiation that was revealed to be captured and documented was very minor than Chernobyl. So I want to talk about Chernobyl. I'm going to show you guys a really cool video. It's very sad though. For the one in Pennsylvania, the 3 Mile Island Unit 2 that's documented on here, it says during the 13-year studies of people who lived within a 5-mile radius of it, only one single death occurred as a consequence of thyroid cancer. And the death was not attributed to radiation exposure. So they couldn't even pinpoint one person that died from the explosion. So I'm not really sure why it's in here other than the fact that it's in the United States and they wanted to put something that happened from the United States in here. When did this one occur? This one occurred in 1979, so it's pretty recent as well. And the NRC, which is the Nuclear Regulatory Commission, reported that the TMI-2, which was the pressurized water reactor, is permanently shut down. So they're never going to use it again because they don't want any kind of an overheating or an explosion to happen again. You can read about it if you want to because it is local-ish because it's in the States, but really Chernobyl is much more interesting. And it says more than 200 people working in the Chernobyl plant received a whole body dose that was excessively 30 to 40 times more radioactive than Hiroshima or Nagasaki. So very, very interesting. Kind of a weird culture shift there because we talked about genetic breaks that can happen. It's really sad because the people there who were exposed were kind of shunned. Then the people that were local didn't want them to have children because their children were being born with defects. Lots of different retardations and things like that, but the people were really injured and there was not a lot of governmental help or assistance. It was kind of just like people were dying on the streets or walking around with limbs falling off their bodies from the explosion and there wasn't any help. And the people that were directly affected, like I said, they were almost shunned or treated as lepers. So I'm going to show you guys a video so you can see what actually happened in Chernobyl. I put both of these up on your canvas too, so hopefully you can see them. I also put up a large module last night for financial aid, scholarship, and student support. I didn't know if you guys had this. If you want to look at it, you can. There's some scholarship opportunities. I obviously know you only have one semester left, but if you want some money, you can apply for it. There's a link for TRIO, which has a scholarship here. They're local to this campus at North if you want to stop by. And there's also student emergency funds that are able to be released. Has anybody heard about that? Okay, hopefully you have. If you can prove any form of documentation like, I don't know, any kind of hardship, if you've had a laptop break within the COVID experience, or I don't Oh no. You need access to a new printer. You can document your hardship, and they will provide you a grant for up to $500. A grant for up to $500, and you just have to send in the application, but it's on there. So it is the second one, student emergency funds. This is funds that the college received from the government for COVID relief. So utilize them, right? They're there for you. Student emergency funds, so click on it. There's also a child care access grant if anybody needs child care. Hopefully you have all of this since you're almost done with the program. I know you're just now meeting face to face too. Alright, if you want to watch these later, you can too.
In the early morning of the 26th of April, 1986, the Chernobyl nuclear power plant in the former Soviet territory of Ukraine exploded, creating what is usually described as the worst nuclear disaster the world has ever seen. The disaster spread radioactivity into the atmosphere in one of the largest bursts of unintentional radioactive release into the environment. Russia, Ukraine, and Belarus were subject to significant exposure following the event, and the rest of Europe was on red alert. Years of independent research and government investigation followed as the world tried to calculate the extent of the damage caused by the disaster. Today on the Infographic Show, we take a look at the aftermath of this tragic event and see if the event was as disastrous as first predicted. Let's take a look at the worst effects of the Chernobyl disaster. Just over 8 miles north of Kiev and about 12 miles south of Belarus, 4 reactors stood next to a reservoir fed by the Pripyat River and close to the town of the same name with a population of 50,000 when the disaster struck. The town of Chernobyl was inhabited by 12,000. And the rest of the land surrounding the plant was predominantly farms and woodland. Water from the Pripyat River was used to cool the reactors. As in most nuclear power plants, the reactor used at Chernobyl, the RBMK-1000, is now, however, well known to have a design flaw in the cooling system. On the 25th of April, plant operators were making preparations for a maintenance shutdown. In the early hours of the 26th, hot fuel rods were lowered into the cooling water, creating steam, and owing to that design flaw, a power surge caused an explosion, killing 2 plant workers. For the following few days, emergency crews attempted to contain the fires and radiation leaks. As more plant workers became exposed to the radiation, they later died of radiation sickness.
So these people who contain the actual radiation and the fire were documented as heroes in this, and they saved basically the entire country because they were willing to sacrifice themselves for the amount of radiation. So they did their best to contain it, cover it with lead. They were shielding it and trying to shield everybody from the dose, but they all died within the plant.
But fortunately, most of the radiation leaked had a relatively short half-life of 8 days. A day after the event on the 27th of April 1986, the town of Pripyat was evacuated. Many of the town's people suffering headaches, vomiting, and other indications of radiation sickness. In the months following the event, 28 plant workers died, and this number grew to 31 after 3 months. In addition, over 6,000 cancer cases have been linked to the event. However, the true number of cases attributed to the event are near impossible to calculate, as people naturally suffer from various cancers. Many doctors in Eastern Europe advised pregnant women to abort their unborn children for fear of them bearing children with birth defects. Although in hindsight, the level of radiation exposure was probably too low to have caused any such complications. The trees in the surrounding woodland were killed from the radiation, and the region became known as the Red Forest, owing to the color the flora turned after the radiation exposure. The contaminated trees were torn down and buried in purpose-dug trenches. Shortly after the disaster, birds living in the area were found to have developed with smaller brains. Swallows in the area demonstrated albino plumage, deformed feet and tail feathers, and tumors. Some cattle born after the event exhibited signs of radioactive mutation. In 2011, though, the Ukraine opened up the area to tourists wishing to see firsthand the effects of the disaster. The region nowadays has become one of the world's most thriving wildlife sanctuaries, hosting thriving numbers of deer, wolves, boar, elk, bear, eagles, and other species scarcely found in other surrounding regions. Despite this recent explosion in fauna, experts predict that the area will not be fit for human habitation for another 20,000 years. Post-disaster, children seem to have been most affected in the form of a thyroid cancer outbreak, caused by the absorption of iodine-131 into the thyroid gland in children in Ukraine and Belarus. Studies show that adults were less affected, and the children who were the youngest during the incident were most at risk. Before the event, the cases of thyroid cancer in Belarus were under 1 case per million people. By 1995, cases were up to 100 per million per year. Clearly, the nuclear event was to blame for this upswing. In West Germany, Down syndrome peaked for some 9 months, with a cluster of 12 cases born in January 1987. That may have been connected to the disaster. In 2006, a group of 8 UN agencies, including the World Health Organization and the International Atomic Energy Agency, along with hundreds of scientists and health experts, assessed the damage of the event. The number of fatalities has not reached the tens of thousands that were predicted shortly after the disaster. Fewer than 50 deaths have been directly attributed to the event. 9 children died of thyroid cancer thought to have been caused by the disaster. The report concluded that, by and large, we have not found profound negative health impacts on the rest of the population in surrounding areas, nor have we found widespread contamination that would continue to pose a substantial threat to human health. It's interesting to note that over 1,000 reactor staff were heavily exposed to radiation, and around 200,000 workers were involved in recovery operations, yet only 50 died from cancer 20 years later. But we aren't out of the woods yet. Scientists are divided in predicting the number of cancer deaths we can expect over the next 20 years, with a report suggesting that a further 4,000 people will die of cancer. The town of Pripyat is still considered uninhabitable, although popular with dark tourists who venture into the zone to see firsthand how the event changed the landscape. Radiation in large volumes kills living things, but amazingly, the flora and fauna surrounding the plant have learned to thrive and in some cases benefit from the radiation. For example, a fungus exists that uses radiation to produce its own energy source, much the same way solar panels use sunlight. This radiotrophic fungi performs radiosynthesis using melanin pigment to convert gamma radiation into chemical energy growth. So while Chernobyl was undoubtedly a disastrous event, we've learned much about the dangers of nuclear radiation as a consequence, and hopefully this knowledge will help us understand nuclear energy better. So what do you think about the Chernobyl nuclear disaster? Was the event as terrible as what we first thought? Let us know in the comments.
Alright, so that's kind of your synopsis for Chernobyl. Really a horrible event though, and something that at first they thought was going to kill everybody in the surrounding areas, but didn't. Interesting fact that your book will tell you is even the milk was somewhat radioactive from the cows, and the cows that were born after the effects. So they were fetuses at one point inside the mama cow had them. Then when they started producing milk years later, the milk was still radioactive. And the amount of radioactivity found in people's actual milk containers in their fridge within 5 miles of the accident was insane as well. So people didn't know it at the time, but they were drinking and eating radioactive food after the accident. So that was probably the largest accident that's occurred that's documented at least. So let's take a break before we go into pathology. Any questions? Anybody dead? Anybody alive?
Before the test, are you gonna do like any type of, just like, not necessarily a review, but just things that we need, like, cause you don't do outlines or anything?
Usually not, no. Sometimes I use PowerPoints, but it really depends on what I'm teaching. If this was in a PowerPoint, it would be very dry and boring. So I would rather just go through the actual information that you need to know.
What about like a review before?
Sure.
The test, just like key points that we need to.
Yeah.
Okay.
Yeah, we can do that.
Just cause I feel like we cover a lot before the test.
Yep. If we need to do that, we absolutely can. All right, go ahead and take a break. 9:50. All right, so come back at 10:20. Take a break, grab something to eat, grab a snack, go to the bathroom.